First, we explain the main motivation for introducing disturbance observers. Over here, you can see a block diagram of a classic feedback control system. All the signals are in the complex Laplace domain. That is, whenever you see S on this block diagram or somewhere else in this tutorial, you should know that S is a complex Laplace variable. C of S is the transfer function of the controller. P of S is the transfer function of the plant. R of S is the reference signal, and Y of S is the output. E of S, that's equal to the difference between R of S and Y of S, is the control error. F of S is the control input to the plant, and finally D of S is the disturbance. The goal of the control algorithm is to make sure that the output Y of S tracks the reference signal R of S despite the negative effects of the disturbance D of S. Let us suppose that C of S is a PID controller. And here is the fundamental question. Can PID controllers reject time-varying disturbances D? For example, let us assume that D is a time-varying disturbance, such as a sine signal or any harmonic signal or even a stochastic signal. And the main problem and the main question is, can a PID controller reject such a disturbance? This is a fundamental question, and the answer to this question will reveal the level of your understanding of control engineering and control theory. Consequently, before you continue to watch this video tutorial, stop for a second and think about this problem and try to answer this problem. If you know the answer to this question, and if you know the correct answer to this question, then congratulations, you have a very deep understanding of control theory. Otherwise, if you have some doubts or if you're not sure, don't worry. We are going to clarify this problem in this video tutorial. The truth is that in the most general case, the classical PID controller can reject constant disturbances or slowly varying or almost constant disturbances. The classical PID controller does not perform well when disturbances are non-constant or time-varying, and this is very, very important. Let us explain this with the following example. Let us assume that our plant is a second-order system. This is a classical oscillator. Then let us assume that PID controller is tuned, and let us for the time being assume that the disturbance is constant. And here is the Simulink block diagram, and as I mentioned previously, I created a separate video tutorial explaining how to simulate this particular example as well as disturbance observers in Simulink, and a link will be provided in the description below. Over here in this Simulink block diagram, we model this disturbance as a constant equal to 2. The reference signal is equal to 1. Here is our PID controller, and here is our transfer function. Now, if you simulate the PID controller, you will see this behavior. The desired output is equal to 1. And over here you can see how the output behaves in time. It goes like this, it has an overshoot, and then it slowly approaches 1. From here we can see that disturbances are rejected and the set point or reference tracking is achieved. Now, let's change this example. Instead of a constant disturbance, let us assume a harmonic disturbance. In particular, let us select disturbance to be equal to the sine signal, in particular sine 4t. Then let's use the same PID controller and let's see the results. Over here you can see the behavior of the output when the disturbances are present. That is, when our system is being affected by non-constant or time-varying disturbances. We can observe that we cannot reject harmonic disturbances, and secondly, we can observe that we cannot achieve set point tracking. And this is a fundamental limitation of the PID controller. This motivates the need for introducing disturbance observers. As you will see later on, disturbance observers are capable of handling this case. That is, they are capable of almost completely rejecting time-varying disturbances. In the sequel, we present the main ideas of disturbance observers. This block diagram represents a basic structure of disturbance observers. In this figure, Q, shown over here and over here, is a transfer function of a low-pass filter that is a design parameter and that's selected by the user who designs the disturbance observer. P minus 1 is an inverse of the transfer function P. That is, P minus 1 is the inverse of our plant. The main idea of the disturbance observer is to introduce a feed-forward disturbance compensation loop, shown over here, that will cancel the disturbance d of s. This is achieved by estimating the disturbance, and the disturbance estimated is denoted by d hat of s. Let us focus on this block. The transfer function of this block is equal to the product of Q and P inverse. That is, the transfer function of this block over here is the product of our Q low-pass filter and the inverse of our plant. The Q filter should be selected as a low-pass filter that satisfies this property. The limit value, when the frequency omega goes to 0, of Q of j omega should be equal to 1. Over here, Q of j omega is obtained by substituting S by S is equal to j omega in the expression for Q of S. As you will see later on, this property of our Q filter will have a very important consequence. In fact, this property will enable our filter to work in practice. Then, the filter Q should be selected such that the relative degree should be greater than or equal to the relative degree of the nominal transfer function P. The relative degree of a transfer function is a difference between the order of the polynomials in the denominator and in the numerator of the transfer function. For example, if our P transfer function looks like this, then the relative degree is equal to 2. This is because the order of the polynomial in the denominator is 2, and the order of the polynomial in the numerator is 0, and consequently 2 minus 0 equals 2. Let us now see what is the consequence of this main property of our Q filter. That is, let's see what is the consequence of the fact that the limit value, when omega is equal to 0, Q of j omega is equal to 1. This means that for relatively low frequencies, our block diagram of the disturbance observer looks like this. How did we obtain this graph? Well, for low frequency, instead of Q, we can simply assume 1. Consequently, we are left with P inverse, and this line becomes simply 1 over here. Okay, let's go one step further, and let's denote all the signals. Let's start from here. Here is the output of our plant. This output is fed to this block P inverse. Over here, after the disturbance is being cancelled, we will have f of s. Since this f of s goes inside of the plant, y of s is f of s multiplying p of s. Now if we multiply this result by p minus 1, over here we will obtain f of s. On the other hand, let's assume that the estimate of our disturbance is exact. That is, that the estimate d hat of d of s is equal to d of s. Then, over here, the signal will be f of s minus d of s. Then this signal is propagated through this line, then the sign is inverted, and consequently we have d of s minus f of s. Then we add f of s, and as the result we obtain d of s. Okay, so d of s is the feed-forward disturbance estimate. It's being added with the negative sign to our f of s, that is to the output of our controller. Then over here at the entry point of our disturbance to the system, d of s and minus d of s are cancelled, and that's the main idea of the disturbance observer. That is, by estimating the disturbance and by adding this disturbance with the negative sign to our output of the controller, we are able to cancel the external disturbances, that d of s. And consequently, over here at the input of the plant, we are only left with f of s. That is, we are only left with unperturbed output of our controller that's computed by the control algorithm. Now, spend some time studying this graph, since this graph is very important for understanding how disturbance observers work in practice. This block diagram is introduced for better understanding of disturbance observer, and it's not completely realistic. First of all, over here we assume that the estimate of our disturbance is exactly equal to the true disturbance. This is never the case. Then, over here, we assume that we perfectly know the transfer function of our plant. In reality, this is not the case. We only know a nominal model, that is, we only know a nominal transfer function. A more realistic block diagram of disturbance observer is shown over here. Let's explain the difference with respect to the previous block diagrams. Here, you can see the complete feedback loop. And over here is the structure of the disturbance observer. First of all, instead of P inverse over here, we have Pn inverse. Pn is a nominal transfer function. That is, this is a transfer function that is known to the control system designer. And again, always keep in mind, the exact model of the system is never known accurately. What we know is only the nominal model. That is, we only know the nominal parameters. For example, if you have a mass spring damper system, you might know only the nominal value of the spring constant. For example, the spring constant can be equal to 100. However, in practice, the spring constant is 110. That is, you have 10% of model uncertainties. Pn will take the value of the spring constant that you actually know. That is, Pn will take into account 100 and it will not take into account 110. Then over here we have an estimate of our d, and this estimate is denoted by d hat. Let's perform the mathematical analysis of our disturbance observers. First of all, the output of the plant y of s is equal to the plant transfer function p multiplying d plus f minus d hat of s. Then, the control output or the input to the plant, f, is equal to control transfer function multiplying the error. Then, if we go back, we can see that the error is equal to the reference minus y, and that's precisely this equation. Then, if we go further, and if we substitute error inside of this equation, we will obtain that f is equal to c transfer function multiplying r minus y. And then, from this part over here, we can express d hat of s like this. Let me explain how we derive this part over here. This signal over here is f of s minus d hat of s. Okay, Now over here you have a minus sign and you have a Q transfer function, and if you just follow this line, you will obtain this part over here, minus Q F multiplying F minus D hat. Then we have this plus part over here. That is, you add Q Pn inverse multiplying Y. That is, you add this part over here. Now, from these several equations, you can express D hat like this. Next, from these equations, we can obtain the transfer functions of our system. Namely, we can express the output y of s as a sum of wd multiplying d of s. Wd is a transfer function from the disturbance to the output. Then we have plus over here, transfer function wr of s. This is the transfer function from the reference signal to the output and multiplying r of s. And that's it. It is easy to show that from these equations, wd of s and wr of s are given by these two equations. Next, let us analyze the reference signal to the output transfer function. First of all, we start from this equation over here. Now, the filter Q of S is selected as a low-pass filter with this property over here. The limit value when omega frequency goes to 0, Q of j omega is equal to 1. And let's use this property. Namely, let's take a limit when omega goes to 0 of WR. And let's see what happens. If we substitute the expression for WR, we will obtain this expression over here. Then, since this part holds exactly, instead of Q we can simply type 1. Then we can proceed further to obtain this equation. Then over here we can see that Pn and minus Pn are cancelled, and consequently we obtain this equation. Now we can cancel P and P, and consequently we obtain this equation over here. Now, let us interpret this result. From this equation, it follows that for low frequency or asymptotically, the closed loop system with a disturbance observer behaves like a closed loop system formed on the basis of the nominal plan. That is, the closed loop system formed on the basis of Pn. This is because the closed loop transfer function from the reference signal to the output for the nominal plant is actually equal to this part over here. In this way, we are able to control the system accurately despite the presence of the model mismatch between the nominal model and the true model. That is, if the controller C is designed on the basis of the nominal plant model Pn, and this is always the case, then for low frequency or asymptotically, the controller will be able to control the true system represented by the transfer function P, that is the transfer function of the true model, as accurately as controlling the nominal model. That is, in the limit, the closed loop transfer function becomes the closed loop transfer function of the nominal system. And this is one big advantage of disturbance observer. That is, disturbance observers are able to cope with model uncertainties, and it looks like we are controlling the system by knowing the exact model of the system. And this is a big advantage since we can guarantee stability and we can guarantee many other things. Then, let's analyze disturbance signal to the output transfer function. Again, we start from this equation and we take the limit when omega goes to 0 of omega d transfer function. Now, due to the fact the limit value for small values of omega of our Q filter is equal to 1, we can see over here that 1 minus 1 becomes 0. That is, disturbances are rejected. To conclude, we have shown that for low frequencies or asymptotically, the disturbance observer is able to attenuate the effects of disturbances. In fact, a disturbance observer can estimate disturbances accurately if disturbance frequencies are in the bandwidth range of the low-pass Q filter. That is not only for small frequency, but if disturbances are in the bandwidth of our Q filter. Consequently, the bandwidth of the Q filter should be set as high as possible. Now, if you analyze this loop over here, you will see that this might not be a good idea always. Namely, if you increase the bandwidth of Q, then you will enable the measurement noise over here to propagate inside of your system. Consequently, there is always a trade-off between disturbance suppression and immunity of your system to the measurement noise. In fact, over here you will have to add a filter that will filter the measurement noise. Okay, let us illustrate the performance of disturbance observers by using an example. And over here we use the same example as the example that we used to demonstrate that PID controller cannot suppress harmonic disturbances. So let's make the situation to be more realistic. First of all, here's our true model. However, a control designer only knows the nominal model. And you can see over here that we have significant model uncertainties. For example, over here the true value is 25, however our control designer assumes 49. And over here you can also see that you have a difference in this term over here as well as the difference in this term over here. And Pn is exactly this part over here that is inverted. Next, we selected the Q filter that looks like this. To select this Q filter, we took into account two requirements. The first requirement is that the limit value when j omega goes to 0, or when omega goes to 0, of Q of j of omega should be equal to 1. And that's precisely the case over here, and you can convince yourself by substituting S by j omega and taking the limit value when omega goes to 0. The second requirement is a relative degree requirement. The relative degree of our nominal model is 2. Consequently, the minimal value of the relative degree of our Q filter has to be 2, and consequently we assume this form of the Q filter. To double check everything, we multiply Q by Pn minus 1, and we obtain this expression over here. And this expression is a proper transfer function. Consequently, this transfer function and the corresponding filter can be implemented in hardware. And this is a very important requirement. That is, the relative degree requirement for our Q filter enables us to actually implement the filter in practice. Okay, let's analyze our Q filter. So here's the Q filter, and notice what I did over here. I deliberately pushed the bandwidth of the Q filter to the right. This is a very important requirement, since I want to increase the frequency range that we can suppress by our disturbance observer. Now again, if we have the measurement noise of the system, this might not be a good idea. However, for simulation purposes, I'm doing this. So we expect that our disturbance observer will be able to reject the disturbances in this frequency range. For example, up to 20 radians per second. Okay, let's go further. Here's the Simulink block diagram of the disturbance observer, and as I mentioned previously, I created a separate video tutorial on how to implement this Simulink block diagram, and the link will be given in the description below. Let us briefly explain this block diagram. Over here we introduced disturbances. Disturbances are simply sine 4t, that is, omega is 4, and this omega is actually inside of the bandwidth of our Q filter, so we expect that we are able to suppress this disturbance. Here's my true plant in canonical form. That's why you see omega n squared, zeta omega n. Omega n is natural undamped frequency, and zeta is the damping ratio. And over here I implemented Q inverse Pn, and you can see the standard form of the disturbance observer. Here I assumed a PID controller, the same PID controller as in the previous case. And voila, here are the results. First of all, for comparison, over here I'm presenting the result obtained by using the pure PID. As we discussed previously, the pure PID cannot reject the sinusoidal disturbances, and this is what pure PID is doing. However, here are the results when we are using disturbance observer. So this case here is comparable. We are using the same PID controller in the same case, and the disturbances are the same. The only difference over here, and when I say only, I mean under quote, is that we are using disturbance observer. And you can see how disturbance observer is able to nicely attenuate this harmonic disturbance. And this is truly, truly amazing. You see the power of disturbance observer. To be honest, I'm really surprised, that is positively surprised, by the performance of disturbance observer. And I suggest to everyone to try to implement disturbance observers in practice. In fact, this is not hard. What you need to do, you just need to find the model of your plant, then compute this filter over here, and then on the basis of this filter, you can simply implement this block as well as this block, and then if you're using the standard PID controller, you can combine this output over here with the output of your PID controller, and you can try to reject the disturbances. Okay, that's all for today, and thanks for watching.